This is an introduction to exponential functions presented by NVCC. It is a fairly commonplace experience for us to hear that something or other is growing exponentially. It may start out really low, but there it goes, it's getting to be really big. Well, that's a way of speaking about something called an exponential function. And an exponential function has this form: y is equal to b some base raised to the power x. So let's compare this with a polynomial y is equal to x to the n, and talk about what's special about exponential growth. Even with a very small base, the value x is going to get bigger and bigger and bigger. So we might have 1,000,000 up here in the exponent, whereas if we have 1,000,000 in the base, it's still being raised only to a fixed power. So it can get only so big at a time. This one grows faster every time. Sooner or later, an exponential function surpasses any polynomial function. Now, I should note here that in this picture, my base is strictly greater than 1. And again, this picture illustrates what is called exponential growth. Let's look at an example in the calculator. In my y equals screen, I'm going to use just the base 2 here, keep it simple, and raise 2 to the power x. So now my variable is in the exponent rather than in the base where we have always seen it up to now. I'm going to graph this, and now I see a function that is asymptotic to 0 on the left and growing very rapidly on the right. Let's look at the table to get some idea of this growth. Well, okay, it doubles each time. So by the time x gets to 10, it's already 1,000. By the time x gets to 20, we have 1,000,000. Now, the flip side, to the left of the vertical axis, we have, when x is equal to -1, 1/2, 1/4, 1/8, 1/16, when x is -10, 1/1000, when x is equal to -20, 1/1,000,000, and so on. So let's take another look at the graph there. This graph gets very close to 0, but it never will reach 0. Let's look at some characteristic properties of this function. So, as we have noted, it's asymptotic to 0 where x is negative and grows indefinitely large where x is positive. So, in short, the domain, it never ends on the left and never ends on the right, so the domain is x is any real number. The range, let's see, the range, x never does reach 0, and it has no maximum. So the range is 0, open on the left, and also open on the right. Or we could say y is any positive real number. Now the bases that we have shown, well, we had an abstract base, except where we actually had base equal to 2. the base can be anything. The base most commonly is one of two things, and these are the two things that it's allowed to be in the calculator. I mean to say that we have already keyed into the calculator. In yellow here, let's suppose that this is y equals e to the x. E is that number that is between 2 and 3, an irrational number that in pre-calc we used a bit, but we said we couldn't tell you what it means. This is the natural exponential base. And then in orange, I'm showing y is equal to 10 to the x. So, what about them? Well, 10 to the x grows a lot faster for positive x, and it runs towards 0 a lot faster for negative x. And observe that the point 0, 1 is on both graphs. Why? Because b raised to the power 0 is equal to 1 for any real number b. There's another very important idea with exponential graphs. Oops. I beg your pardon. Another idea of great importance is that of exponential decay. Now, exponential decay has a graph that looks a lot like the graph of y equals b to the x. But instead of growing as x gets larger, it shrinks as x gets larger. Now, from our study of pre-calc, we know that if we want a graph to take this action of being spun around the vertical axis, let's say that f of x here is b to the x with b greater than 1, then the second graph that we drew, we would produce it from f of x by making the input to the function negative x. So in this case, b raised to the negative x power, where b is greater than 1. Okay. Examples of exponential decay include a drug in the bloodstream fading away, radioactive decay. If you put a radioactive isotope on the counter and let its half-life, which might be measured in seconds or in centuries, pass, and come back and measure how much you have again, you'll have only half as much as you had before. And then after the next half-life passes, you'll have a quarter of what you started with, and so on. And then another example is temperature. There's something called Newton's law of cooling, which says, let's see, here's room temperature on the dotted line. Put a hot cup of coffee on the counter. Its temperature approaches room temperature in an exponential decay fashion. Okay, so that's the end. Oh, no it isn't. Let's have a look at b to the negative x. So this is an exponential function because it has the base and it has x in the exponent. And by the rules of exponents, this is equal to b to the power negative 1 raised to the x. I multiply these two exponents together. And again, by the rules of exponents, that's equal to 1 over b to the x. Okay, so in other words, if we have 2 to the negative x power, that's equal to 1/2 to the power x. Okay, so it's easier to think about if we just say that for any exponential function, it's defined as y is equal to b to the x greater than 1, but in fact b can be any positive number that is not equal to 1. I'm going to let you think about why it can't be equal to 1. And then we need to keep in mind, if b is between 0 and 1, we're going to have a graph that looks like that. That might be easier to think of as something raised to a negative x power. If b is greater than 1, then our picture looks like that. Okay, so that is the end of our introduction.